All right, guys, so welcome to a new semester. I hope that you had a good rest because as it says on Dante's hell, entrance to hell, it says abandon all hope, as you are with me. And if you were here with my students from last semester, you would have understood exactly what I mean, but it will take a little bit of time. So the syllabus, this is what you should be able to access on my website. My website is etkin.com, and the syllabi are stored in a separate folder. I will not use Blackboard for most purposes, and for a simple reason, it's that it's made by CUNY, right? So I will not use Blackboard for that reason already. So you have whatever the links over here. You have syllabi here. And spring 2021, you see this is the information for this class. You should be able to join before me, although maybe not access the meeting before I get there, but you should be able to be in the waiting room, right? It should also be a waiting room without me, that I should be allowing you to go in, but somehow it doesn't work. So that's the meeting ID. I will also be sending you links. And the office hours for this class, again, you have this, this is my email address. I requested that you send me an email detailing your first name, last name, that you're a stats student, and what are your interests, what do you love, what excites you, or what you're afraid of. It's all fine. That's optional. So that is to be sent to this email, please. I need you on my mailing list. That's how I will communicate with you. And my website, where you see all the materials, all the homeworks, or the exams posted, will be at etkin.com. I will see, maybe I will collect your exams through Blackboard. I will see about that, but I cannot promise if that's the way I'll do it, or through email. Okay, office hours always after class. If you really want to, we can sometimes do them before class. The main thing is that you should solve a lot of problems, and you should discuss those problems with me. Good? Discuss such problems with me so that I will be able to maybe help you and see where you're stuck and explain if you want something explained. Hello, James. Nice to see you. I'm glad that you all made it. Now, the textbook is a first course in probability theory, but I will read out of my own notes, which should be self-sufficient. This is maybe a supplementary text, and I have a copy of it on my website in case you want to access it, okay? So this book is for supplementary exercises, for reading on, whatnot, but I will be mostly reading out of my lecture notes that are posted on this website. So our learning objectives in terms of this book are chapters 1 through chapter 6. We will probably not finish chapter 6. It's a lot of information. I will be spending a long time on the first several chapters. 1 through 5 will be most of the semester. I tend to not be able to move fast enough, as combinatorics are difficult. Good? So homework. On my website, there are homework problems, and there are practice exercises and everything like that, which I will not collect, but which I encourage you to do, and I encourage you to discuss those problems with me. How, not only if you solve it correctly, but how you solve is very important. Good? So the grade is going to be based on 3 exams. One of them is the final. So exam 1 covers the first 2 chapters, exam 2 covers the next 2 chapters, and the final is cumulative. It will cover another 2 chapters, kind of 1.5 truly. I will not finish chapter 6. I never am able to do that fast enough. And that will be 40% of your grade, the final, okay? So 30, 30, and 40. Usually, I would have given take-home exams, the first 2 as take-home exams, and the final as an in-class exam, and that would be my control for prevention of cheating, yes? But in our circumstance, it's completely inefficient to look at what you're doing through the internet. It's not working very well, and besides, I'm able to detect if you're cheating or not much easier, because there is you see, people always betray how they solve the question when they don't know what they write, and especially when they don't know anything at all. There is a sort of, first of all, lack of consistency between one question to another. So they might have solved correctly a very difficult question and entirely incorrectly a very simple question, or that they have a sort of very strong repetitiveness, and many other factors. So if you are interested, in my, of course, great naivety, I thought that probability students are there because they enjoy probability, because they are interested in the subject and they have no reason to cheat on my exams. However, last semester, I discovered about, I would say, 50% of the students, they posted questions online, and I found the questions that they posted, of course. And also I could see how they wrote on those questions. So I have several procedures against that. One of them is, first of all, I might notice it. You can decide whether I will or not. It's up to you. You will risk it. But if I catch you posting the exams, if I decide that you posted any question, even one question from my exams online, you will fail for that exam. And that would mean at least 30% off. Now, I personally do not enjoy, this grading thing. It's very weird for me, or prevention of cheating is also very weird for me. I think truly either you understand the material or not, and that's pretty much the only thing that this class gives you, hopefully, right? Helps you understand the material. The only reason I get so irritated by cheating is because I then sometimes feel that I'm assigning a very good grade if I don't catch those people, like A+, to a person that did nothing at all in this class, spent not a single moment thinking about it, and assigning a bad grade to somebody who truly strived and struggled. You understand? And that is basically a very personal thing, truly, right? It gets me annoyed. Not to mention that I actually spend a lot of time describing this material and trying to explain it. And, of course, the exam questions that I answer, that I see that are compromised, I cannot reuse them in the same way, and that creates extra work for me. Policing you creates a lot of extra work that I completely do not enjoy, and therefore this semester, this semester I'll be a bit stricter about your showing attendance. So I will, first of all, try to gauge what you do. I might do that also by discussing one-on-one problems with some of you. Especially after some exams, I will just see how much do you know, like an oral exam, right? You might have a session and I will see how you answer questions. The best way to avoid any such things is to avoid any suspicion whatsoever that you copy exams, any sort of indication that you do so, okay? And of course, showing me your faces is a good way to start, because then I know who am I talking to, right? And what expressions, I can see expressions on your eyes. When I'm in a class, I can see whether you understand or not, whether you're confused or not. When it's a black Malevich square, I am not sure. If, of course, your circumstances are uncomfortable, you don't have a room, or, it's too noisy, or some other situations, I do not want to force you to do that, but I ask you to do that, okay? For now, ask you, and I will take attendance, and the attendance will indicate whether or not you are showing up in class and whether or not you are showing your face, okay? So you decide if it means anything or not. Good? This is the way the grade is distributed. If you want to know how I calculate it. So once I get the average, I look at those numbers and I will assign the letter grade according to this rubric. Good? Of course, if I know you, that's another thing. If I know and you worked, and I could see that you did something, you worked hard, let's say, it would be maybe a C, but I see if I pushed a little bit, it can be a C+. If it's a B-, I pushed a little bit, it can be a B, I will do that. But I will do that more so for people that I am sure worked in my class, that actually put in effort, okay? That I know personally. So it's very good idea to know me personally, as it's always true with anybody you interact with. Okay, so show me your good side. I already mentioned what is about academic dishonesty, and I mentioned about attendance, right? So I personally do not punish you for not attending a class, but I will this time record it more so than I recorded it last time. I will just write, okay, this person came 1, 2, 3, you know, and last semester I had people swearing, you know, false accusations, and they don't even know what sort of things they are caught in. Understand? So I was extremely irritated with policing. And of course, I can show you what is the dog-headed people, if you know what it is. What is oprichnina, you know? So do not create that situation. Do not create Tsar Ivan the Terrible, which I hope not to be. Good? That's it for the syllabus. Good. Now we can take a good deep breath and begin with today's lecture, and hopefully enjoy the material. Enjoy it. It's very interesting. It's so deeply amazing, as I hope you noticed from the questions that I asked in the email last night. Yes, Grant? Yes, good. So have you looked at the questions, guys? Yes, wonderful. Besides, I'm sorry I jump around. Tell me anything in the syllabus not clear, anything I need to clarify for you, anything that worries you too much. Again, guys, it's a very simple but very difficult to define thing. I want from you goodwill, right? I want to think, well, you are truly trying to understand the material and you are honest with me. You're not trying to deceive me. You're not trying to, you know, you're not creating paranoia basically in me, okay? That's all. So here, the material is posted under Stat 311 probability theory. There you will see exams. Those are the exams probably from last semester. Homework, prior exams. I will change this, of course, right? I do encourage you to look at those tests. And if by some chance you think my exams are extremely difficult, you can discuss them. You see, I always thought I wrote those questions and my God, it's like I bake a beautiful cake for my students, but they didn't enjoy it as much as I imagined. I think, oh my God, my darlings, my beautiful, smart darlings, you solved it. You solved it actually. And then I realized, no, they did not. They posted it. And also many of the solutions that they submitted were completely idiotic because the people that answered those questions for them did not understand the material. And that's the first way that I immediately know that somebody is cheating, right? Is that the solution that they present is extremely inconsistent. It's idiotic, in other words, right? The solution does not work. And it doesn't work in the same way with many people. Anyhow, so before we proceed, let's just see why probability is so, as the Germans say, heimtückisch, or very, that's the word, very, yeah, it's shadows. It's very, very sinister, very, something that sneaks at your back without you expecting it. And so let's look at this question. And that actually,
hello?
Rest a little bit here in calculus lecture, okay? I asked you those questions. Have you thought about those questions that I asked in my email? You did?
Hello?
Yes?
Hello, can you hear me?
I can.
Can we call you by your first name or your last name?
It doesn't matter. Call me the blob. As long as you know the material, that's all that I care about.
All right. This is Fiona Henry. I thought we were going to discuss about the movie that you wanted us to watch.
Well, I mean, we can discuss all of those. That relates to, look at the 12 Angry Men. All right. I'm not gonna, let me just explain something. So the email that I sent you, that part about the movie was especially true about what was happening in the summer. I might not have the same time to discuss those ideas, but I want for you to think about how convinced you are that something is true. How convinced you are that something is true. And that would be the question that we will address right now, okay?
All right.
Okay, cool. So this is a very similar question to the one I posted in my email. Very similar. The one in the email we will address later in the semester, okay? So here is my first question. You are invited to a household known to have 2 children. you have never seen these children and have no prior knowledge of this family where you're invited. You know nothing about them. You just come in and you know they have two children. Maybe you're a police officer, perhaps, right? And you're called to investigate the situation, and you know that there's a family having two children. As you park your car, you notice that one child is playing in the yard and that she is a girl. Question: what is the probability that both children are girls? Now, think about it a little bit and write your answer. I want to see what you would say. Okay, we begin having 1/4, 0.25. Melissa says 1/4. Faria says 1/4. Alan says 50, 1/2, I see. 1.2, somebody said. Maybe probability is never more than 1, guys. So 1/4, 1/2. So many interesting numbers. 1/4. Go on. Yeah, so again, guys, it's not a sociological question. It's not about how many genders there are. You can assume it's being a boy or a girl is equally likely. So in other words, before you observe an entity, a child, I call it entity because I don't like children. Before you observe it, it is the probability of it being a girl or a boy is 1/2. Okay, let's see. Roadra, and I'm sorry. You see, I spoke German too much, so I almost started talking to you in German. That will happen very frequently until I readjust. Okay. So 1/2 because one of the girls is confirmed a girl, so we have only 1/2. That's an interesting, Rwanda. Thank you for your contribution. And Anton says 1/4. Any other answers? Any other answers? So I think we have more or less a consensus, at least in this category. Either the answer is 1/2 or the answer is 1/4. Would you all agree that that's true? Would you, in other words, be partial to that consensus? Yes? I want to see. Yes, 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 yes. That's very nice. That's very nice because, and that relates to 12 Angry Men, because imagine that you are the jurors and this was something that you truly cared about, truly important to you. You know, right now you're able to think about it because your emotions are not involved. You could not care about this problem. You don't care if it's 1/2 or 1/4 or anything else. You don't care. It would not bother you, right? You just care to get the right answer. But in this situation, even where you are impartial and you do not care, you are all of you wrong. Every single person that answered is incorrect. The probability is neither 1/2 nor 1/4. And that is why I will need to teach you something that CUNY should have taught you, bureaucracy, or the Kafka Protocol. It will be our first few lectures. Okay. 0 or 1, no. 3/4, well, no, not 3/4. Okay, now let's explain what and why, and later we will address those ideas. That's why initially the class will be very simple, but very quickly it will become difficult. Okay, and I will encourage you to try to solve the problems the way I try to solve them, because that's my way of making a protocol and avoiding mistakes when I can make such protocols. Here is the answer. The answer is actually 1/3. And I will try to later explain to you deeper why the answer is 1/3. You imagine that each girl is an object. Well, you are probably nice and wonderful people, so you don't think of girls or boys as objects, but you think of a universe. What you do in probability, you count universes. you were counting the wrong universe. What you have seen is that your universe is consisting initially of 4 possibilities. That's why initially both girls being equal to 1/4 would be, sorry, both children being girls is probability of 1/4, because you initially have 4 universes with equal possibilities of happening before you make an observation, you see? So when you are told you're visiting a family that, that has 2 children, assuming that each child is equally likely to be a boy or girl, you're facing this possibility. You're facing the possibility that you are observing boy, boy, or boy, girl, or girl, boy, or girl, girl. You understand? So you, when you're visiting this family, will end up in one universe, and this universe is very simplified, ignoring everything else, right? Ignoring what color grass is in the backyard, what's the building, what model car were you driving, and just focusing, somehow hyper focusing on 2 creatures, on boy or girl. Okay, so that's why some of you said 1/4. Implicitly, you were saying that you are equally likely to be in one of those 4 universes. But you make an observation and you see that one is a girl. One of the children is a girl. So which of those possibilities are eliminated? Obviously, the possibility boy, boy is eliminated. Now you are in any one of 3 universes. And each of those universes are equally likely. The probability that both children are girls is 1/3. 1 out of 3 universes. Do you understand?
Professor, can I ask you something?
Of course, as always.
Can we also assume that since boy, girl, and girl, boy are the same, can we think it like that or no?
But they are not the same. That's a very, very good comment. They are not. Because if the children are different, one was born first, the other was born second. So maybe this is the youngest and this is the oldest, or vice versa. Doesn't matter how you list them, right? So I will teach you how to do that a bit more. I just want to first show you that you have to think this way. Okay?
Can I ask a question about
that?
that?
Of course, Sarah, by all means.
Because if we're assuming like, oh, the boy is older, the boy is younger.
Yes.
But if there's a sister, she's also a different person. So it could be she has a sister that's older, a sister that's younger. Wouldn't that
Yes,
matter?
well, it was not part of the information. True, if I know that's the oldest, if I see the oldest child, if what I'm observing is the oldest child, the probability now becomes 1/2. Because if the oldest child is a girl, then there are only 2 possibilities: girl and boy is second, younger child, or girl and younger child is also girl, right? So it could be 1/2 with extra information. But my point is, why did you make a mistake? Because you focused on a part of the universe rather than the full universe. When you do probability, you have to count all the possible universes, or sometimes reduce that, because all the possible universes involve so many factors.
Sure,
right?
but the girl that's playing outside could be the oldest girl or the youngest girl.
Yes, but I don't know that from this information.
You only accounted for one situation in which, right? Unless we're assuming that the girls are identical.
No, so it's no 2 objects. That's an assumption. That's a philosophical assumption. Probability that you can take is that no 2 objects that are different in space-time. If anybody took philosophy and read Kant, no 2 objects that are different in space-time are identical, right? Because it's maybe not true. Who knows, right? But if they don't occupy the same position at the same time, they're not identical objects. So 2 girls are not identical objects. Even if they are identical twins, they are not identical. Okay, so I can imagine that one is older, the other is younger. I imagine there is some distinction that I am observing. Okay, and in this problem, I have not mentioned which girl I have observed. Was it the oldest girl or the youngest girl? Only that I observed the girl. That means that the probability is 1/3, because we have 3 universes which are equally likely. Don't worry about it. We will cover that at length when we talk about probability. First thing is combinatorics. How do we count things? Good?
Wait, I got a question.
Go ahead, James.
So couldn't you say, because you said it's the full universe, right? So here's my thought process, right?
Mm-hmm.
So so to me, I think when you have BB, that is the full universe, right? But it has a let's say accommodation or a sentence rule, right? So the way I see it is that if it doesn't have at least one girl, then we cannot accept that into our universe in a
So
way.
yes, we basically we are entering one of four rooms or one of four universes, right? Because we have observed that that universe contains at least one girl, it cannot be this universe which I crossed out. So we have only three possibilities, and because we believe that each of those possibilities is equally likely, because we believe that each of those possibilities are equally likely, we will say that the probability that both are girls is 1/3, because only one of those three universes corresponds to the desired outcome of both girls. Okay, now I'm going to clear this board and I'm going to ask you one more question. Okay, one more question. Those are the same questions. I mean, what I sent in email, they're exactly of the same type. Now, her mother comes to greet you and she goes, you know, she talks, yaps around, and then says, this child that you're observing was born on Wednesday. What's the probability that both children are girls? We're assuming whatever, you see, this is a mathematical problem. So we're not assuming anything physiological, right? We're just assuming everything you can imagine assuming. Each child is equally likely to be born on any day. There is no preference to be born on Sunday, Monday, Tuesday, you know, even maybe it's not true. So still 1/3, I say, same probability, 1/3. Victoria says, a lot of people say 1/3 and I'm so proud of you, right? So nice that you say 1/3. Because obviously being born on a Wednesday has nothing to do with with having two girls, correct? Yes? We are all agreeing, yes, guys? That's the 12 angry men that I'm talking about, right? We are having irrefutable evidence. Science, we believe in it, yes? Andres says 50%. What is point TP? I do not always know your young people lingo.
It's just a mistake.
Ah, okay, typo.
Right.
Yeah, let me just check. You see, I cannot remember. You see, sinister is not completely the right word, but let me see, how do you say that? 1 second. Are you there, guys?
Yes.
Okay, good. You're thinking? Sorry, I say I try to multitask, but I'm very stupid when I try to multitask. I'm just, you speak Russian? What is kavarny if you speak Russian? If you speak German, can you translate to English the word tückisch? Tückisch, no? because that's what probability is. Anyhow, so we all agree that I think one person says 50% and a bunch say 1/3. Well, let me tell you what's the probability. The probability is 13/27. No. Yes, none of you were right. Yes. You see? So that's why it's very important.
50% is close to that, though.
Huh? Yes, 50% is somewhat close. I didn't say it's not, but doesn't matter. We don't care about close, right? We care about exact. Because close, I mean, close is wrong.
Fair.
Exactly, right? And that's not the question here is we usually estimate probabilities. They're very difficult to solve exactly. The point is to understand what probability is eventually. Yes? So let me explain what you did wrong. Well, what you did wrong is you assumed that, you assumed correctly that, you know, Wednesday does not have, being born on a Wednesday does not affect your gender. Okay, so somebody wrote to me it means vicious. So vicious is not the right word exactly, that's good. But probability is more than vicious. It's something like this, something that sneaks in your bag. Коварный, right, in Russian, that's a good word. Vicious, too aggressive, I think. But thank you. Treacherous, insidious, thank you, insidious, yes. Probability is insidious, like me, right? Precisely. So this is what you actually have to now assume. Now that you have information that a person was born on a Wednesday, you are correct in understanding that this is not affecting the gender, but you are thinking incorrectly about the problem. What born on a Wednesday does for you is that it identifies the universe better than without this information. Every piece of information that you ever betray, every single thing that you ever say will reduce the number of potential universes. You understand? So what happens when you say anything, when you express anything, the potential becomes more and more actual. When you make an observation, it becomes actual. You follow? So you never knew what I was, but now that you look at me, there is less potential, right? It's more something determined, something definite. Same thing happens here. So in general, if you are taking into account the birthday of a person, then we're dealing here with this universe. At least there's of course a danger of is it the right universe to deal with? We talk about it later. But we have this universe. We have oldest child, the day of birth, youngest child, and the day of birth. You agree with me? So there are 4 inputs into that universe that is available to me. So I am looking at possibly oldest girl that was born on a Wednesday and knowing nothing about the youngest child and the day on which this child was born. Or I am observing the youngest child that was born on a Wednesday. Do you see that? So either I can fill in those 2 inputs or the last 2 inputs. Clear? And how many universes do we have like that? So look at it. In this case, you have 2 possibilities, boy or girl, and times 7 days, so 14 possibilities. Do you agree? 14 possibilities where the universe begins with girl, Wednesday. 14 such universes, potential universes. And we have 14 potential universes where they end in girl, Wednesday. Youngest girl, born on Wednesday. Those 2 universes have one overlap, and the overlap is girl, Wednesday, girl, Wednesday. So I calculate 14 plus 14 minus 1, because I counted one universe more than once. You don't have to necessarily write the entire sample space, but yes, that is the important part here, is that we have 27, right? We need to know how many possibilities. Writing out the sample space can be extremely difficult. Okay, so we know here that there are 27 universes that I might be observing. I'm observing exactly one of 27 possible universes. Are you with me? And I need to know which of those universes correspond to both being girls. Both being girls is the universe of the form girl, Wednesday, girl, can be born, the other girl can be born on whichever day, Or you see, here I know the oldest girl was born on Wednesday. I know the youngest is a girl, but I don't know the day. And here I know everything about the youngest girl and nothing about the oldest girl. So how many possibilities here? Here there are only 7 possibilities, and here another 7 possibilities, and there is 1 overlap. Again, girl Wednesday, girl Wednesday. So it's 2 times 7 minus 1, 13 possibilities. So for both being girls, it's 13 universes now out of 27 possible universes. So the answer is 13 over 27. Yes? Interesting. Yes, guys, that's what I will be teaching you. I sounded like a robot. Well, maybe I am. What do you want me to repeat? Again, guys, there are 27 possible universes. 13 of those universes satisfy the condition that both children are girls. Do you understand? Okay, don't worry if you're confused yet. It is a sort of flavoring. I'm trying to explain to you why you want to be doing probability the way I will teach you until you get very comfortable with it. Why you would want to do something I call Kafka Protocol. And if you want to know why I call it Kafka Protocol, read Kafka's The Castle, das Schloss. Good? Now, I will not go through the full lesson. In case you want to read more about it, it goes into something that some of you will find controversial, and that's where the the third man, or the 12 angry men, comes into account. Is that this was a question where all of you made a mistake and you did not care about the answer to this question. Now imagine I introduce a question where you are extremely biased, where you really care one way or another what's the answer. And then your ability to think is even more compromised. Okay. And yeah, so in my opinion, see, what's interesting about probability is that in some sense it frees your mind to think about things that like other subjects do not explain, like other disciplines do not. Still you will make mistakes, still you will be biased, that's not avoidable. Still you will be obsessed about whatever truths you believe, which might not be truths. But yes, if you're interested, you can look at those videos. I haven't updated it since last semester, and that was my lecture for calculus. The problem is that's called Why Do We Need Proof? Okay, lecture for calculus, and that's at Math 150 at limits. You see, calculus lecture notes, Math 150 at limits. I made it out of the desire to try to attract calculus students to mathematics, because what they do is not always as fun. Good. Now let's go and begin talking about probability. And we begin from the very, very beginning, where it's very simple. Good? And that is combinatorics. Yes, Erin? Combinatorics. So here is where you find them, guys. Stat 311 probability theory. Probability lecture notes, combinatorial analysis, basic principle of counting. How do I count universes is what I have to figure. So we begin with the most simple situation. Coin is flipped. So there could be only 2 possible outcomes, head or tail. Okay, so if my coin is my potential universe, then the actual universes that can come out are 2, head or tail. Now, if I take a coin and I flip it, and in addition to it, I toss a fair die, it doesn't have to be fair, it's just a die, right? Then I have those possibilities. So a coin can display heads and the die can display any one of the numbers 1 through 6. Or the coin can be tail and the die can display any number 1 through 6. Good? So altogether I have 12 universes. 6 universes for heads and 6 universes for tails, yes? So we want to understand how many universes arise where you have two procedures, and each of them creates, what first procedure creates m potential outcomes, procedure 2 creates n potential outcomes. Good. What is the number of total outcomes if I perform one experiment and then the other? So the idea is this: for every outcome in the first experiment, let's say if the outcome was outcome 1, any number of n possible outcomes are possible. Are you with me, guys? You understand what I'm saying? Not confused yet? Because at any moment you're confused, you let me know, okay? Okay. The outcomes of experiment 2 do not have to be independent of the experiment 1. Maybe they are entirely different if 1 comes out or than if 2 comes out. What matters is that if outcome 1 comes out, you have n possibilities. If outcome 2 comes out, you have n possibilities, and so on. So here is what you can do. You can arrange them in this matrix form where the row, we have the row represents outcome on experiment 1 and the column represents the outcome in experiment 2. Yes? And now notice, we don't know, Grant, if it's dependent or not. It could be dependent, it could be independent. In other words, the result of experiment, well, let me possibly skip for one moment and show you this. So imagine that you have, what you do in experiment 1, you select a woman, and then for her you select one of her children, and each of our women have 3 children. Okay, so naturally the outcome of experiment 1 is which woman do you select, woman 1, woman 2, or all the way to woman 10. You understand? Depending on which woman you selected, obviously you will have a different group of children, right? So but basically every woman in this case has 3 children. So for every outcome of experiment 1 of picking the woman, you have 3 outcomes for experiment 2 of picking a child. Do you understand? Usually if you just take many women, some of them have 0 children, some of them have 1 children, some have 2 children, and onwards, right? So we are considering here the situation where the outcome of experiment 1 will not influence the number of outcomes in experiment 2. It might influence the actual outcomes, but not their number. Are you with me? Yes, everybody understands that, right? So the outcomes could be entirely different, but the number of outcomes is not affected by what happens in experiment 1. So then how do I count the universes that can arise from experiment 1 together with experiment 2? So in our case, the universe is outcome on experiment 1 and outcome on experiment 2 all together. That's my universe, okay? So I can list the universes based on outcomes of, the rows represent the outcomes of experiment 1, the columns represent the outcomes of experiment 2. And do you see what I have? I have how many rows? I have 1 row, 2nd row, m rows, and each row has n inputs, right? Each row has n columns. So it's n times m or m times n, however you prefer to call it, right? So the answer is m multiplied by n. Do you see how I did it? I just see that I have here, I can do it by columns or by rows. So if I do it by rows, I see 1 row, 2nd row, let me write it. I see 1st row, 2nd row, all the way to the mth row, right? Mth row, that means that, that the first outcome is m, outcome number m. Mth row, and then how many do we add? So here we add plus n, here we add plus n, here we add plus n. How many times do we add n to itself? We add it m times n times, right? We add it m times. Do you understand why it's m multiplied by n? Why I multiply? It's never arbitrary. Okay, so when you're doing probability, why do you multiply? It should never be arbitrary. All you're doing is counting. You should understand how the counting is working. Good. So again, let's see with a very simple exercise. There are 10 women. Each woman has 3 children. If one woman and one of her children are to be chosen as a mother and child of the year, how many different choices are possible? Please calculate and let me know the number. Okay. Good so far. All right, so you see that the answer is 30. Everybody sees that, but not only for this question. Make sure that you understand this question is easy. You have to ingrain in your mind how is it that you're carrying this procedure. And knowing German can be helpful because you can then understand how to be a very efficient bureaucrat. So here is how I'm gonna do this procedure if I were a German bureaucrat or ein deutscher Beamter. So what you do is this: you assign a number to each one of the women. So woman number 1, 2, 3, all the way to 10, right? And you assign a number to each of her children, 1, 2, or 3 in this case, yes? And then you create this document, okay? Mother, child. And what you do in this document, you put in the mother number and you put in the child number that was selected, right? So that's a document. And what you are counting is the number of documents. Make sense? You're counting how many documents are in this full pile. Each document represents the actual selection. It represents an actual universe, actual selection. So this represents mother number 4, child number 2. And maybe you rank the children by age, maybe oldest, middle, youngest, okay? Good, so then how many such documents? By the basic principle of counting, experiment 1 is filling in the first box. So instructions, you first have to fill in this box, then you fill in that box. Good. So there are 10 possibilities for the first box. How many inputs? 10 inputs for the first box. And then once you have an input, there are 3 inputs for the second box. 10 times 3 by basic principle of counting is 30. Clear? Now we can generalize that basic principle of counting to an arbitrary number of experiments. So experiment 1, experiment 2, experiment R. And what happens in each case is that the outcome of experiment 1 does not affect the number of nodes for the next experiment. Okay? They do not. They might be dependent experiments. The results might be different depending on what happens here, but the number of nodes are not. Internet unstable. Can you still hear me? Am I coming through?
No, we can't hear you, Professor.
Yes. Am I coming through again?
We lost you after you.
Yes.
Yeah, you're back.
I'm back, yeah? Yes. Inconsistent. Yes. I don't know what to do about it. I'm sorry. Good. Okay. Are you with me, guys? So I hope I'm not over-explaining or under-explaining, so you let me know, right? So here is the general situation. We have R experiments. I hope you understand abstraction here. R experiments, 1, 2, 3, all the way to R. And each of them has some number of possible outcomes. And the universe will be the collection of all possible, well, the collection of specific outcomes from experiment 1, from experiment 2, and from experiment R. How do I figure out the total number of universes? Well, you can do it this way. You can always group all the experiments together except for the last. You can always reduce it to 2 experiments, okay? So you can begin by having 3 experiments. You can group those 2 as 1 experiment, super experiment, and then you have just 2 possibilities. So how many outcomes in that super experiment? We know it's experiment 1 times experiment 2 number of outcomes. Do you agree? By basic principle of counting, I know that if I have 2 of them, the number of universes is just the number of outcomes for experiment 1 multiplied by number of outcomes for experiment number 2. Good. So if I have 3 of them, I want to create a sort of very quick, very efficient way to be sure that I know how to count. So I can group those 2 experiments into 1 super experiment and say that performing 3 experiments is the same as performing 1 super experiment, consisting of n1 times n2 outcomes, times the number of outcomes in experiment 3. Again, it's basically reduced to a situation when you have 2, so that would be n1 times n2 times n3. Did I lose you? So you see, even at those stages, you have to be very, very careful, because you've seen you were not answering the previous question correctly, right? So you have to really understand how it all works and understand it so you never have any doubt. Super experiment, Nisha, is it's the number of outcomes for both experiment 1 and experiment 2. Okay, so the way you can imagine doing that, maybe that will help. I hope it will. Let's do this, okay? So you have this document, which you will soon be calling Kafka Protocol, okay? So that's experiment 1. That's experiment 2. And that's experiment 3. Yes? Okay, that you, as soon as you put a number for experiment 1, a number for experiment 2, a number for experiment 3, now the document identifies one specific universe. You understand that the documents are supposed to record one particular universe, each document. Clear? Once I write the information on the document, I right away know what was the actual universe that came to be. So if I put a number in here and I put a number in here, that's a super experiment. How many possibilities for filling just those two? If you have n1 possibilities for experiment 1 and n2 possibilities for experiment 2, that would be n1 multiplied by n2. You see? Exactly. You all see that, guys? So it's not for my full universe. I need to put something in here. But now look at it. I just use induction because now this is the super experiment. To fill out simultaneously experiment 1 and experiment 2 box, I have n1 times n2 possibilities. And then this one has n3 possibilities. And we know, again, by the basic principle of counting, which only deals with 2 categories, one category and another category, right? Here I have 3, so directly we don't have the basic principle of counting, but I can easily reduce to it. So it's n1 times n2 times n3. Do you understand the idea? It's an argument by induction. Once I know how to count for only 2 experiments, I know how to count for arbitrary many experiments. I can just group by 2, then group again by 2, then group again by 2. I expand first 2 boxes, then first 2 boxes in the third, then the 3 boxes together in the fourth, and onwards. Do you see that? Yes? Yes, yes. And I again, you might wonder, well, you can understand it. It might seem very simple to you. Be careful, right? Nothing in probability is simple. Probability is insidious. So you have to be sure that you understand those principles when it starts and understand them rigorously, so you have no doubt. So that's why we make such fuss about this situation where it seems not to be too bad. Right? So here is, so in general, for the general principle of counting is n1 times n2 times nr. If I have a bunch of boxes, if I have r boxes, I just multiply the number of possible inputs, first box, second box, onwards. Good? How many different 7-plate license plates are possible if the first 3 plates are to be occupied by letters and the final 4 by numbers? So there are how many letters? There are, I think, 26 letters in the English alphabet. Yes. So you don't need to, you can just write the formula, right? What do I do? Okay, somebody already replied. Grant, thank you. And Jennifer, thank you. All right, so the answer is obviously, here is the Kafka protocol, okay? Kafka protocol, because in Germany, everything is a protocol. If you cross a red light, it's a protocol. So you have here 26, 26, 26. Right? Those first three have 26 possibilities each for the letter. And then the remaining ones have 10 possibilities each. So it's 26 to the power of 3 times 10 to the 4 by the generalized basic principle of counting. You with me? I hope you are, guys. Make sure that you are. If you are ashamed of anything, worried about anything, you talk to me after class. It's very simple again. It's very simple to talk to me, I think. At least I talk to myself all the time. It seems not to be too difficult. You know.
Where are you getting the 10 from?
The 10, because there are 10 numbers. The last 4 are supposed to be numbers. Numbers are 0, 1, 2, 3, all the way to 9. So 0 is like replacing 10. So you have like 1, 2, 3, 4, 5, all the way to 9. That's 9 numbers, and 0 is the 10th number.
Okay.
You see it? Exactly. Very good, James. So good. You see that, guys? Okay. How many functions defined on endpoints are possible if each functional value is either 0 or 1? Do you understand what that means? In other words, a function is you have the numbers. The number 1 is assigned to something, the number 2 is assigned to something, and 1 is assigned to either 0 or 1. 2 is assigned to either 0 or 1. 3 is assigned to either 0 or 1, onwards until we get to some n. Yes, okay. 2 to the n, exactly, right? So there are basically 2 possibilities. 2 possibilities, 2 possibilities. So you see what happens. So first you have 2, then you have 2 squared, then you have 2 cubed. And if you reach n, you will have 2 to the power of n. Clear? Wonderful. Super experiment. So the way, if I had to do it, so rigorously, I would possibly write this. So you have 1, 2, 3. So I would do like this. So first, those 2 possibilities, it's 2 squared, right? And then I group it together. This is a super experiment. 1 and 2 is a super experiment having 4 possibilities. And 3 has only 2 possibilities. You see? That's how I do the grouping, Grant. Clear? Okay. So this is the Kafka protocol. In other words, the document is 1. The input 1 was carried to what goes here, 0 or 1. 0 or 1. Once I fill in all the boxes, I have a particular function. Because if I say all of it is 0, that means that the function maps everything identically to 0. If everything is 1, the function maps each number to 1. Okay, and this, of course, this function has to do a lot with what? With attendance. So for example, if I have here 40 students, how many possible attendance rosters can I have? If I write the function f of x equal to 0, that's a code for nobody has bothered coming to my class. If I write f of x equal to 1, that means every single person came to my class for any x, right? Because person 1 came or not, 0 if the person did not come, 1 if the person came. So there are 2 to the power of 40 possibilities for the attendance. It's huge, right? So the possible attendances are enormous for 40 people. Okay. Now here is, now we can begin talking about permutations. And the idea here is how many ways are there to arrange n students in a row? And here I represent the situation. We have student 1, student 2, student n. Good. Presumably students are distinguishable. I find it hard to do. I don't remember names, and faces, apparently I cannot tell them apart. So that's why I assign numbers to my students. Student 1, 2, 3, 4, right? All the way to student n. And I assign numbers on their position. So when I place them against the wall, I can imagine there are markings on the floor. First marking, second, third, that's the queue line. First in line, second in line, third in line. Good? So, and here again, I mentioned that philosophy. The philosophy is that even if the objects look alike, since you are occupying different positions at the same time, you are not identical objects, even if I cannot tell you apart. All right, guys, is it back to normal? Internet? My internet, is it working okay? All right, sorry for the disruptions. Yeah, of course, for now, everything is for now. It's all contingency. Don't ever make plans. Useless. All right. So this is what I just said. Even if objects all look alike, by the virtue of them occupying different places in space at the same time, I can presume those objects are not alike. Not exactly the same, to be precise. So how many ways to put n people in a queue line in order? 1, 2, 3, all the way, like that. You want to answer it before I do? Okay. 2 people said right away n factorial, but of course, why? Yes. So we create our protocol. In our protocol, we can ask who is in first place. And there are n students, so the first box can be occupied by n inputs. Yes, order matters here, n inputs. Yes, second box can be occupied by n minus 1 inputs. You see, because one person was removed, n minus 1 inputs. And so we have n possibilities for the first experiment, n minus 1 possibilities for the second experiment. You all understand that, guys? If you need a numeric example, you let me know. Right? N possibilities, n minus 1 possibilities. Once I fill those, then I have less and less possibilities, always one less possibility. So I just multiply, here it's written, n possibilities, n minus 1 possibilities. The very last is going to be 1 possibility. So you multiply by the principle of counting, n minus 1 all the way to the last multiplication is by 1. Good? With me? You all see what's happening here. It's because of the protocol, right? So I count how many universes are possible. So here is an instance where the outcome of the first experiment is what number do I put in this box? It's 1 through n. The outcome of this first experiment will influence the outcomes of the second experiment, yes? But not the number of outcomes, you understand? So if I put here the number 1, the possibilities will be 2, 3, 4, all the way to n. If I put the number 2, the possibility is just everything but excluding the number 2, but always the same number of outcomes. The outcomes are influenced, but they're always the same number of outcomes. So then I can utilize the principle of counting. Are you all with me? Yes? Yes, if we cannot reuse the same number, Grant, obviously, right? So you cannot stay in 2 places in line at the same time, right? You cannot be the first in line and the 7th in line. So that's why you don't reuse it here. Okay. So here is a question, guys. Let's try to answer it. Class has 6 men and 4 women. Students are ranked according to their performance from best to worst. How many different rankings are possible among all students? So that's question number A. And you can answer question number B right away if you want to. How many rankings if men are ranked by themselves and women are ranked by themselves? You don't mix women and men. You don't compare women with men. Yes. So, Sarah, you can ask this question. Men and women, right? If they are in different places at the same time, they are not the same object. That's the philosophy we adopt for combinatorics. And I think, Sarah, your last name is missing a C and an E at the end. It should be Weinflasche, which means wine bottle.
It's my family does it with a Z and an E.
Mm.
I don't know if that's different.
All right, so we have two answers here. So I see a lot of 10 factorials, and I see somewhere a 24 factorial, okay? Erin, I see, good. All right, guys, so let's solve it together. Ready? Guys, so you understand it's not only the question that you're trying to solve, but the technique. It's more important than solving this question, right? Is to understand how we approach the questions altogether, some general method of getting there. So first, for the first part, I can use this Kafka document. In the Kafka document, I just assign all the people. I have 4 women and 6 men, I think. Yeah. So I assign each of them a number, 1 through 10, their human number, right? And then in my protocol, I say who is the first in line, who is the second in line, third in line, onwards. I just put a number here. Yes? All right, it lets me know that I'm logging already when it's over, I guess, right? To just make me feel bad. Can you hear me now, guys? Back again? So I assign a human number to each of my 10 participants. And I rank them together. So that means this is my universe will be the ranking of all of them, right? Who is the first in line, who is second in line, onwards, right? So there are 10 possibilities for first in line, 9 possibilities for second in line, 8 possibilities for third in line. You see what I'm saying, right? So there are going to be 10 factorial possibilities, 10 times 9 times 8 onwards. And this is a code. This is a particular code. I look at it and I know person number 3 is first, second is third, first is third, well, second is second, person number 1 is third, and onwards. You see what I'm saying, right? So this is a code that tells me where the people are among themselves. Good? And now, would you please rehash what would happen for question number B? I do not compare women and men, but the universe is the ranking of the men together with the ranking of the women. Make sure that you see that. What sort of document do you visualize? What paper?
Could we say here that we visualize 2 experiments really, and one with just men, the second with just women? So we'd have 6 factorial for just men, following the same logic as part A, and then 4 factorial
Yes,
for just
exactly.
women.
Excellent.
And then to merge them together, we would multiply, in this case, 6 factorial by 4 factorial.
Very good. By the way, guys, if somebody writes 6 factorial times 4 factorial, or 4 factorial times 6 factorial, obviously, because numbers, when multiplication, they commute, the result is the same, but are they having the same protocol? Are they using the same document, strictly speaking? Well, Elisa says yes, because what I want you to understand is this: when I look at your solutions, what I try to do is visualize what procedure did you use. In other words, I imagine I am counting a pile of documents. That's what I always imagine doing in basic combinatorics. I imagine counting pile of documents, and then I look at the document and I want to know what sort of form does it have, you see? How is the information placed in the document? The information, once I read it, I am supposed to know what universe took place. You understand? The document is a report of the universe that took place. Make sense? We will talk about it deeper and deeper as we go on, because I mean, obviously universe is very complicated. It doesn't have only these things happening, right? You might have those people were ranked and it was summertime and birds were chirping on trees. And that document is not reporting on birds chirping on trees. So how is it reporting on every possible universe? So those are things that we will still need to consider later on as when we talk about conditional probability, okay? But in principle, what the document is reporting is which universe became actual, which universe took place, okay? And we will develop that idea. So that was the document I used for first protocol. I mean, there is a guideline. You assign numbers to each people. So number 1 means Sarah, number 2 means Jeffrey, I don't know, right? And onwards. And I just rank them. Now, how would I do the document for the second procedure? So I have one category, which is men, and they are assigned men number 1 through 6. And the other category is women. They're assigned woman number 1 through 4. So I place men on the left and women on the right. Now we have an experiment here for men. It's 6 factorial outcomes. Experiment for women is 4 factorial outcomes. You see the boxes are the experiments. So there are, in this case, I can basically group small experiments into super experiments, and I can just have this type of process, right? So I know it's 6 factorial because I perform the generalized principle of counting for the men, right? And I do the same for women, it's 4 factorial. So it's 6 factorial times 4 factorial. Yes? But if I were to write 4 factorial times 6 factorial, and I were just writing how I'm doing the document, that means that women are on the left and men are on the right. Do you see what I'm saying? So it means, technically speaking, very technically, of course, is that it's a different document. So every time you solve a combinatorial problem, but you do not do it the same way, it might be correct, but it might mean that you're using a different counting procedure. There are many. Do you understand? So when you're counting something, what I visualize, what I try to visualize at least, is what document you are using. What does your document look like? And of course, when you indicate it on your exam, that makes it a bit easier for me to verify whether you're right or not. You have to specify what procedure do you use to record all the possible universes, where one document records one universe uniquely. Clear? Okay, here is the next example, guys. We're almost over, just a little bit more. We'll finish this lesson, the easy lesson. You wish to arrange 10 books on a shelf. There are 4 math books, 3 chemistry, 2 history, and 1 language book. Am I back? All right. You understand the question, guys? How many possibilities are there if the books on the same topic must stay together? Do you see that? So you have 10 books altogether. You have 4 math books, 3 chemistry, 2 history, and 1 language book. In how many ways can you arrange them on the shelf so you can see, so that books stay together? Books on the same category, guys. I see somebody says 4 factorial. Books on the same category must stay together. Okay. Be careful. Yes, Jennifer, and always write yourself a document. I want you to imagine a document where you fill in this information, because that will, even if you can do this particular problem in your head, which is good, you need a procedure for you to verify that you're not making a mistake. You understand? I'll show you my document, but you should always have a document in your mind. Okay, Shulamit, that's very nice. All right, I'm gonna tell you what it is, guys. I'm sorry I give you so little time, but we have enormous amount to go through. If you stay in class, after class we can do practices always, right? We can take a lot of time to think about the problems. Okay, 1 second. Yes, Grant, I didn't say 10 factorial should be the right answer. So here is how I imagine this to be done, right? So how do you arrange? When you observe the books of the same category are together. So the first part of the document tells me what categories I see in which order in my document, you see? So I assigned math to be 1, chemistry to be 2, history as 3, and language as 4. That's the code for category. You understand? So if I first see math books, I will see 1 in this category, right? If math appears on the last, I will see 1 in this box. Make sense? So this does not tell me the arrangement of the books, only the relative arrangement of the categories. So there are 4 categories, and there are 4 factorial ways of filling in the first boxes. For the math, there are 4 math books, so there are 4 factorial ways of filling this. There are 3 factorial ways of filling box grouping number 2, 2 factorial ways of filling box grouping number 3, and 1 factorial way of filling box grouping number 4. Yes? Do you understand? If I read this code, can you see that, guys? Some of you are programmers, but can you see that that if I read this code, I will right away know how the books are arranged. And if the books are arranged in a particular way, I can translate them in a one-to-one fashion to this code. That's not a unique code. You might try another one. But some of you notice, many of you wrote 1 4 factorial less than necessary. It should be 4 factorial times 4 factorial times 3 factorial times 2 factorial times 1 factorial. Many of you wrote only 4 factorial. Many of you wrote 4 factorial times 3 factorial times 2 factorial, which is not exactly right. And so you understand it's very easy to make a mistake when you don't see the situation as I try to explain. Okay, here is my code. 2, 4, 1, 3. 2 means I begin, when I move left to right, I begin seeing category 2. So I first see, where is it? I first see chemistry. Okay, you understand? So I read this code and I now know how the books are arranged. It just basically, this is the math books. Take them and place them in this region. Take the chemistry books, place them here. Clear? How that works?
So you always have to, even though it's only 1 book, you should always write 1 factorial just for like the.
You don't have to. Once you're good at it, you don't have to do any of it. My point is that you should have in your head right away a very efficient procedure for you to be sure that you're correct. Some counting methods are going to be better than others. Many things you can skip, but especially when I teach you combinatorics, you want to learn a general way of doing that so you avoid mistakes. It's very, very easy to create mistakes. And that is my Kafka protocol. You could have placed this category anywhere else. So for example, if you wrote 4 factorial times 3 factorial times 2 factorial times 1 factorial times 4 factorial, you will be correct. It's the same thing, but very technically speaking, it's a different procedure. They look very similar. I just place this box somewhere else, but the document looks different, right? I want to see that you have a visual on the document, that you see how the document appears. Good? Are we together, guys? We're good? All right, guys. So I see that you're anxious. Some of you are anxious to leave. You can. Can you hear me now? So the lesson is over. I will post this lecture on YouTube.
You said something, Arkady?
Huh? Yes, I'm saying something.
Can you repeat that?
Yes. So.
Can you repeat that?
Can you hear me now, guys?
Yes.
Good. Apologies for the internet problems. I had other problems in before. So the lesson is over. Just one last question. You all are on my mailing list, correct? Everybody here is on my mailing list. If not, send me a message. Reply to my message that I was sending a few times to your Hunter email address. If you have questions at any moment after class, please stay with me. We can practice and we can be slow, okay? And we can discuss any of your ideas. All right, I'm stopping the recording. I will post it later on YouTube if you want to watch it.